Push OK on the recording. Yeah, let's wait a couple of minutes. Um, I'm sure VJ would come, please.
You tell Matthias about this? Matthias?
Yeah. He said he cannot. Well, he's there, but he said he's teaching. Because of his teaching, he may not be able to show up in person. Could we see the list of attendants also on the side?
Oh, yeah.
Oh, over there. Oh, yeah, that's perfect. Okay, yeah. Sounds good.
Hello.
Hello. What is your name?
David.
David.
Jana. But here,
yeah, oh, that's perfect. Yeah. Okay. Oh, next time I'll send to the whole math department to see if more people come. Just wanted to make sure everything is. Okay, VJ is also here. I guess maybe that's good enough.
Is that a signal to start?
Hi, VJ.
Hello.
Excellent. Okay, good. Yeah, so we have enough people both online and in person. Start. Okay, welcome everybody to the first AI for Math seminar. Hopefully this will be a regular event happening bi-weekly or as kind of people want to. If you have suggestions for speakers, please let me know. So we just want to hear, from all sides of people who want to do something related to math, to AI, or their connection with each other. So we are very happy for our first speaker to have a Prithwish Jana. I hope I pronounce this correctly. And he will tell us about AI for math, Neuro-Symbolic Auto-Formalization into Lean via joint embeddings. Yes, please start.
Yeah.
Thank you.
Thank you so much for having me. So, hi everyone, I'm Prithwish. I'm a PhD student in computer science at Georgia Tech, advised by Professor Vijay Ganesh. And today I'll be presenting a talk on AI for math, this Neuro-Symbolic Auto-Formalization into Lean via joint embeddings. And this talk is about how we can tightly integrate LLMs with automated reasoning tools to improve their precision and reliability. And through some of our previous work in Neuro-Symbolic AI, we have already demonstrated substantial improvements in AI for software engineering, for example, code translation and generation. And in this talk, I'll show how we extend those ideas to AI for math using joint embeddings to enable end-to-end auto-formalization of theorems and proofs in Lean. So starting with the introduction. So in the space of mathematics, researchers came up with computer verifiable proofs that enable machine checkable verification of proofs without any ambiguity. And these are powered by formal languages like Lean, Isabelle, etc. And they use strict syntactic rules and symbolic logic that enables machine checkable verification. However, while it is nice to have these kind of languages like Lean, it's even better if we can automatically generate proofs in a formal language. That's because formalizing a proof requires significant amount of time and expertise. And even for experienced mathematicians, translating a natural language proof to such a formal language is not a streamlined process. So to simplify the process, three key research areas are emerging. The first is auto-formalization, where a natural language proof is translated to a formal language proof. Next is automated formal proof synthesis, where given a formal theorem, we want to produce a formal proof for that. And thirdly, there is discovery of conjectures, where the system proposes new conjectures and identifies underlying mathematical patterns. So together, these three areas, they aim to make formal mathematics more accessible and scalable, and therefore bridging the gap between human reasoning and machine verifiable proofs. And as you all know, AI is already being used to automate various formalization efforts. For example, the DeepSeek prover, Alpha Proof, Alpha Geometry, the Gödel prover, LeanDojo, and so on. So in this space of using AI for mathematics, our long-term goal, long-term vision is to build a unified AI for math ecosystem for different tasks like auto-formalization, proof synthesis, and conjecture discovery, so that it can handle proofs of any size. So the idea is to divide a natural language proof into smaller lemmas and formalize each part step by step. So we also want to use an intermediate representation inspired by Vern or Blueprint that can bridge the gap between natural language and formal language. And thereafter, we want to retrieve semantically relevant formalizations using joint embeddings. So this can allow us to apply retrieval augmented generation effectively. And finally, we want the system to support multiple backends like Lean, Coq, Isabelle. So translating from intermediate representation into the specific proof assistant language. And ultimately, our goal is to populate major libraries like Mathlib for Lean, the Coq standard library, and the archive of formal proofs for Isabelle. And in the remaining part of the talk, we'll focus on the aspect of auto-formalization. And we already built a joint embedding system for representing natural language and formal language in a shared semantic space. And we observed that we are getting significant improvements when this is applied in the space of proof auto-formalization. So in the next part of the talk, I will walk you through our recent work on proof auto-formalization. So first, let me formalize the problem for proof auto-formalization as a learning task. So the input is a natural language theorem proof pair, and the goal is to produce a corresponding formal, that is lean theorem proof pair. And formally, we want to learn a function f that goes from natural language to formal language, that is lean, such that the output lean theorem proof pair, it satisfies two criteria. One is type correctness. So the lean proof should pass all type checks, ensuring it actually proves the formal theorem with no open goals in the DAG or proof tree. And second is semantic correctness. So the formal theorem has to be semantically equivalent to the original natural language theorem. So in short, the system should translate both theorem and proof from a natural language to a formal language like Lean, and it should preserve both logical validity and the semantic meaning. So now let's
Actually,
look at.
can I already ask a question?
Yeah, sure.
So what is semantic equivalence means here? Can you say a bit more what that means? Is that a formal definition for semantic equivalence?
No, actually, because the input is a natural language, so we cannot define semantic equivalence formally between a natural language and a formal language. But here we try to show a best approach where we use an LLM to prove bidirectional equivalence between two theorems. So I will show that in the later part of the slide.
If I can add to Castra's question a little bit,
Mm.
the goal is to be able to show that you can derive the formal statement from the natural statement somehow, and vice versa. Now, this is, of course, almost an impossible task. So we don't semantically state these property, but rather we use proxies to check for semantic correctness, which can have errors in them. But from experience, it's a heuristic that works some of the time.
Thanks.
So now let's look at the landscape of LLM-based auto-formalization tools. So that is systems that translate from natural language to formal language. So most of the existing systems, they focus only on theorem auto-formalization. That is, they convert just the natural language statement into a formal theorem. So for example, the Kimina auto-formalizer, MMA, the step formalizer, Herald translator, all of these are theorem auto-formalizer tools. And all these LLMs, they stop at the statement level and they do not formalize the accompanying proof. And by contrast, proof auto-formulation tools, they focus on translating both the theorem and the proof into a fully checkable formal linearizable proof, and it is much less explored. So for example, the draft sketch and proof paper, so it converts proofs into isable sketches with missing steps and then tries to fill the gaps with sledgehammer. And also there is a tool called Form L4. It is another approach for specific for lean, and it incorporates step level compilation feedback. But critically, none of these approaches, they provide like end-to-end natural language to formal language alignment of theorems and proofs in a shared semantic space, which we try to address through our method. So now let's go through some of the challenges of auto-formalizing proofs. So auto-formalizing proofs is hard for several reasons. For example, first, there is no formal way to check if a natural language theorem and proof really match with the generated formal version. So the input natural language pair and the output lean pair may look related, but we cannot directly verify semantic equivalence. Second, large language models often hallucinate, so they can generate proofs that look plausible, but are actually incorrect or infeasible. Third, aligned natural language data and formal language data is scarce. So without enough supervision of this NLFL data, learning to map natural language to formal proofs is very difficult. Another challenge is that most of the tools, they separate translation from the proof synthesis. So for example, even the alpha proof, which achieved the silver medal performance in the 2024 IMO, so it manually translates natural language to formal language first, the theorems only, then synthesize proofs for the formal language theorems. And further, random few-shot demonstrations, they can hurt semantic correctness. So for example, if we give some random examples in the prompt, they may improve the syntax, but the output often fail to capture the original meaning. And finally, natural language proofs are often incomplete or underspecified, so they can omit steps and rely on implicit. So we have to rely on the implicit context. So
Can I ask a question?
Yeah,
here?
sure.
So it sounds like kind of the structure of what you're trying to do is to take a pair in natural language, so theorem and proof, and then translate that to a theorem and proof in the formal language. It's like you're
Right.
working with the pair together.
Yes, right.
It seems like there might be more data around if you worked just with the theorem as by itself and worked from theorem in natural language to theorem in formal language, and that you're more likely to be able to in the initial stages evaluate the semantic equivalence with the human doing that evaluating rather than trying to deal with the much bigger structure, which is that pair.
Yeah, so when we like do these two tasks separately, like theorem to theorem translation and then proof synthesis from the formal language theorem, I agree that the data might be like there are many more data available when we are doing theorem to theorem translation. But the thing is, when we already have a natural language proof of something or a proof sketch, that helps in the formalization process. So if we have some natural language proof, it is much like the formulation process is much more feasible proof formalization process, rather than starting from scratch from a theorem and asking an LLM to like discover a proof for that.
I wasn't thinking of asking the LLM to discover the proof, but just thinking about asking the LLM to be able to go from the formal language, from the natural language statement of a theorem to the formal language statement of the theorem.
Okay, yeah.
Is
That's
that
the
yeah,
So my
the
question is the same. I think the hallucination does not happen in the TFL and PFL, right? It only happens between the theorem to the first human theorem to the formal language theorem.
for
That's
TNL to TFL, the hallucination can also happen because the TNL is always underspecified. So the hallucination is less. For theorem auto-formulation, hallucination is much less than proof auto-formulation, but there is still hallucination going on.
If I can address the question that was posed earlier, it is true that there is a lot more data available for going from natural language theorem to formal language theorem, like Prithwish said. But just to restate what Prithwish was also saying is that we we have to start thinking about the problem of also translating proofs. Furthermore, as and when it is available, because it makes the model hallucinate less as a consequence. Does that address the question, or?
Well, let's see where the talk goes, I guess, right?
Yeah.
Yeah, okay, so you can continue.
Okay. So up to this point, I've walked you through the motivation or long-term vision and the problem formulation for proof auto-formulation, and also the prior work. And in the remaining part of the talk, I'll describe our proposed method, which is a system called Proof Bridge. And it performs auto-formulation of natural language proofs into Lean via joint embeddings. And I'll first describe the architecture in 3 stages. And after presenting the method, I'll move to the experimental evaluation and compare against the top performing state of the art. And before concluding, I'll also briefly talk about another technique we developed called RLSF. And finally, I'll finish with a few closing remarks, tying all these ideas together. So now I'll go through a recent work titled Proof Bridge. So this is a unified framework that translates entire natural language theorems and proofs into Lean 4. And at its core is a cross-model retrieval system. So given a natural language theorem proof pair, we can retrieve semantically relevant formal language examples from a large database. And this actually guides the auto-formulation process. And here is the overall pipeline for Proof Bridge. So this is just a summary. So first, we train a joint embedding model for natural and formal language using contrastive learning. So this allows us to retrieve a set of related formal language theorem proof pairs for any given natural language input. Next, in the second step, we fine-tune an LLM on the NL to Lean translation, and it is conditioned on the retrieved proofs and the relevance score, so it can learn from the relevant examples. And essentially, the examples we retrieve from the database, they serve as demonstration to guide the auto-formulation process. And at inference time, the system retrieves the most relevant Lean proofs, and the LLM then attempts to auto-formalize the natural language theorem proof pair. And if there is any error detected, we apply an iterative repair loop to refine the formal language pair. And I'll go through all of these one by one. So step 1 of the proof bridge is a natural language to formal language cross-model retrieval. And this is one of the core components of our whole pipeline. So to achieve this, we first train a giant embedding model that learns a shared semantic space for natural language theorem proof pairs and their Lean counterpart. So the goal is to, in the shared semantic space, the goal is to align the semantic meaning across these two modalities, natural language and Lean, so that we can retrieve formal examples that are truly relevant given to our natural language input. So that means similar proofs in natural language and formal language are placed close to each other in the semantic space. And at a high level, the input consists of the natural language theorem proof pair and also a large database of Lean theorem proof pairs. And the model outputs the top K most relevant formal language pairs along with the relevance score. So where K is a much smaller value than the total database size. And the key insight is that these retrieved formal language demonstration, they should serve as guides for the downstream auto-formulation process. And they should capture all the reusable proof tactics, the DAG level reasoning patterns. So that can help the LLM to correctly formalize the natural language to the formal language.
Actually, can I
And
ask a question just here?
yeah,
So we
sure.
like to ask questions. I'm sorry. So can you comment on the architecture that you're using? Like, what do you mean by train? What are
by
you
the
actually doing? Yeah,
Yeah, I'll go through the architecture in the next slide.
you will do it. Okay.
Yeah, I'll go through the encoder, like how we are training the encoders and these things. So to implement the cross-model retrieval, we first define the natural language and the formal language encoder for each theorem proof pair. So the natural language encoder, it maps a natural language theorem proof pair into a vector in the shared semantic space. On the other hand, the formal language encoder does the same thing for the corresponding Lean theorem proof pair. And both encoders produce a vector of dimension D in the shared semantic space. And each encoder is first initialized with a pre-trained model. And for each model, we have 2 sets of parameters. So there is a set of frozen parameters that helps to capture the general language or coding knowledge of the encoder. And whereas the trainable parameters are fine-tuned to align the natural language and formal language semantics for cross-modal retrieval. So first, coming to the natural language encoder. So for this, we use the all mini LM L6V2. So this is a lightweight model with 22.7 million parameters. And this is effective at capturing the semantic similarity in natural language. So what it does is it encodes each natural language theorem proof pair into a 384 dimensional embedding. And we then project that embedding into the joint semantic space of dimension 512 using a linear layer. And the linear layer is part of the trainable parameters. So this allows the natural language representation to align with the corresponding lean proof in the shared semantic space for cross-modal retrieval. Next, before coming to the formal language encoder in this part, so let me briefly discuss about tactic style proofs in Lean. So one of the major advantages of writing proofs in Lean is the support of tactics. And any theorem proof pair has two components, theorem statement. Theorem statement is always like a declarative proposition of the form if premises then conclusion. And we also have the proof, which is a logical argument establishing the validity. And it's represented as a sequence of tactics. So tag 0 to tag k-1 like this. And diagrammatically, tactic style proof is represented as a DAG of proof states and tactics. And at the beginning, so at the extreme left, we start with a single proof state with one open goal that corresponds to the theorem statement. And whenever we apply a tactic, it generates a new proof state with one or more open goals. And finally, there are no open goals to be proven. And these tactics are essentially the high-level commands, so they can transform the proof state to another. So based on this, we develop the formal language encoder. So we first represent a lean proof as a DAG of tactics. Then given a theorem proof pair in Lean, we extract the linearized traversal of the DAG using Lean REPL. So it looks like this. And this produces an ordered sequence of proof state transformations where each state represents a proof step with 0 or more open goals, and the initial state corresponds to the theorem itself. So now to encode the proof, we first encode each state of the proof using the Lean Dojo's by T5 proof state encoder. And it has 218 million parameters. And it produces embeddings of the size 1472 per state. And we then aggregate these embeddings via mean pooling. So we have like embeddings for each proof state. We apply mean pooling and we obtain a single representation for the entire proof. And finally, we project this embedding into the joint semantic space of dimension 512 using the trainable linear layer. So now I've shown how we project the natural language theorem proof pair and also the formal language theorem proof pair. Next, coming to how we train this model. So now as we can project both the natural language and Lean through their corresponding encoders into a shared space of dimension 512, we now need to train the encoder such that semantically equivalent natural and formal language components, they are placed close to each other. So for this, the joint embedding model comes to the help. So it is trained using a contrastive learning loss. And the key idea is simple. So for each positive natural language formal language pair, we want their embeddings to have high cosine similarity, while embeddings of mismatched pairs, they're pushed far apart. And formally, we normalize each embedding first and then compute the cosine similarity between natural language embedding and the formal language embedding, that is the vectors. And during training, we use a symmetric contrastive loss over mini batches so that the in-batch negative, we are sampling the negatives from within the batch. And this loss, it decreases when the positive pairs are close enough and the negative pairs are far apart in the embedding space. So effectively, what we want to do for each natural language embedding, we are pulling it close to the corresponding formal language embedding. And also we are pushing the other embeddings far from those which are not relevant. So this creates a shared semantic space that aligns theorem proof pairs across modalities. So now with the joint embedding natural language embedding semantic space in place, so we can now leverage it to guide the LLM training. So step 2 is that we want to retrieve the relevant pairs and perform a retrieval augmented fine-tuning for proof auto-formalization. So what we do is we fine-tune an LLM. In our case, we use the Kimina Prover RL 1.7 billion model.
Can I just interrupt you for a second?
Yeah,
What,
sure.
what are the, in the shared semantic space, what are the tokens?
Uh, in the shared semantic space, we are embedding the natural language theorem proof pair and the formal language theorem proof pair.
So the tokens are either words or like commands in Lean or something?
In the shared space, you only have vector embeds. So it's like, think of it this way, right? You're given a sequence of tokens in natural language, theorem proof pair, okay?
Yeah.
And you're also given the equivalent one in Lean. And so what you're doing is you're taking these two pairs and putting them close by in the semantic space. The idea is that when you do if the two theorems are indeed equivalent, we want them to be close by. If the two theorems are inequivalent, then we want them to be far apart in the embedding space.
So the tokens
reason
are
for
a
doing that
pair
is-
of theorem and a proof.
Right.
No,
the
that's
theorem,
I
the
see.
tokens. So a sequence of tokens that when you send in a bunch of words into the model, they are tokenized and then they are mapped.
Yeah.
These encoders are mapping it into an embedding space. Okay.
No,
And
I understand.
this
So what are the
mo-
tokens I was asking, like for the Lean language especially?
The tokens are just it's just tokenized by the encoder model. So it's just natural language tokens that we use for any encoder.
So you're not re-tokenizing like because it's a math or something. You just like so what I don't understand, like what is close to what exactly? Like when you write you draw these like blue dots close to a red dot, like what are they exactly? Like what is close to what, I wonder?
So for
Like, there's
example,
no way a Lean, yeah.
in this example, we show two instances, the instance J and instance K. We want the red and blue dots for instance J close to each other. But if the red and blue are from different pairs, we want them far apart.
I think the question is, I think Castro wants you to define the shared semantic space.
Yeah,
What
I kind of
exactly
want to
is
know
in the
what
shared
exactly is
semantic?
going on in there
So-
because otherwise yeah.
So in the shared
Yeah.
semantic,
R to the
Yeah.
D, so.
The shared semantic space.
But it's not enough dimension for all theorems and their proofs. Like is a blue dot representing a whole theorem and its proof?
yes, the whole theorem and its proof, the Lean
So
theorem
and that lives in what dimensional vector space?
512.
Like a whole theorem and its proof is represented by one vector?
Yes, one vector.
Because you're mapping it into a vector. You're taking the stream of tokens and you're encoding it into a vector.
Yeah, it feels like there's not enough space there to encode this much information. It's like feels like the information loss to be too big.
Each dimension you have like a real number axis.
No, I understand, but the number of independent things that grows exponentially with it, but it's still not enough. Yeah, no, I understand that. It's still not enough. Like the number of, I don't know, it's like you're fitting a universe of theorems into a 500 dimensional vector space. I don't think so.
Well, I mean, so as the number of theorems and proofs that you have to consider grows, you will have to consider larger models.
But also at the moment you have like a subfield of math that you're trying to embed or something, right?
At the moment, we are driven by the fact that we have a specific data set
I see.
against which we want to show that our technique as a proof of concept is better
see.
than other techniques and foundation models.
Okay, so the blue dot is really a whole pair theorem and proof. It
Yes,
represents the
right.
whole. Yeah. Okay, I
The
understand.
blue dot is for the Lean and red dot is for the natural.
Yeah,
language. Both are
yeah.
for theorems and proofs.
Very good. Okay.
Maybe we should see an example, but that's probably not in your slide, so that's okay.
Yeah, like for the vector, we can't really show an example because it's just a like vector of numbers.
But I think Castro's point is well taken, right? Because
Yeah,
you
yeah,
want a
right.
larger
Exactly.
model when you're considering really large proofs.
Yeah.
Right.
So next, coming to the step 2 of so here we do retrieval augmented fine tuning for our proof auto-formalization. So thing we want to do, we want to fine tune an LLM. In this case, we are using the Kimina Prover RL 1.7 billion model. And we want to translate natural language theorem proof pairs in Lean into Lean. So for each training example, the input prompt includes the natural language pair plus the top K retrieved formal language theorem proof pairs from our embedding model, along with the relevant score. So these retrieved examples provide rich contextual knowledge, showing how similar theorems and proof strategies are formalized in Lean. And the relevance score actually helps the model to weigh the importance of each example, and it can guide it towards better semantic and syntactic correctness. And to fine-tune the LLM for retrieval augmented proof auto-formalization, we construct this input context containing the natural language theorem proof pair along with the top K retrieved formal language pairs and the relevance score. And the LLM in turn, so LLM takes these two as input and produces a formalization attempt, that is a theorem proof pair in Lean, as the output. And we train the LLM by minimizing the standard autoregressive language modeling loss, which is essentially the cross entropy between the generated formalization and the gold standard Lean theorem proof pair. And this allows the model to learn how to integrate information from both natural language input and the retrieved formal language examples to provide correct, semantically aligned formal language proofs. So here we are just training the model with the cross entropy loss based on the generated Lean theorem proof and the gold standard theorem proof in Lean. And next, step 3. So now we have the model trained. So with the LLM fine-tuned using the retrieval augmented examples, we now move to the step 3, where the model's generated formalization is iteratively refined to ensure both type correctness and semantic correctness before producing the final Lean theorem proof pair. So here we do an iterative proof repair during inference. And because the LLMs are stochastic models, so the generated formal language pairs can sometimes contain syntactic errors or even semantic misalignment. So to address this, we apply this iterative mechanism that combines Lean's type checker along with the semantic equivalence verification through Gemini. And as demonstrated by this diagram, so during inference, the LLM takes the natural language and the top K retrieved Lean objects as input and produces a theorem proof pair in Lean. And now the LLM produce the initial version, and now we perform two types of check. One is the syntactic verification using Lean's type checker. This ensures that the proof is valid. And also we perform the semantic verification. This is to confirm that the formal theorem is kind of equivalent through a heuristic to the original natural language theorem. And the repair loop iteratively refines the generated proof until it satisfies both the type correctness and the semantic alignment.
So just 1 second. So what is the again? What is the feedback on the semantic verification looks like again? Like,
so we are prompting Gemini with the natural language theorem and the formal language theorem and asking it whether they're equivalent or not. And if Gemini says they're not equivalent, we get that feedback, provide it to the LLM, and ask it to repair it.
but the Gemini could be wrong, right?
Yes, Gemini could be wrong.
But so in general, like if you want to like do this in general, you have to like have a human do this eventually, or what is the how would this be scaled eventually?
I mean, I think we'll have to use a variety of different techniques. Yes, human in the feedback loop also would help a lot. The main problem with that is it is much slower.
Yeah.
So you'll have to sort of scale it by making it a community effort. And at the end of the day, there is a process in Lean. The MATLAB library is populated only if the people who maintain the MATLAB library approve of your pull requests. So there is going to be a human in the loop eventually.
Yeah.
Before
No, but I guess my question is, if I ask Gemini to turn something into Lean, they will hallucinate much more. But if I ask him if a Lean thing that is already generated is the same as some natural language, then it's much more accurate. That's what you're saying, right?
Right. Yeah, exactly.
Exactly.
And this is during the inference pipeline, but actually during the evaluation, we have a much stronger metric for semantic equivalence. But during inference, we are assuming we don't have the gold standard formal theorem. So here we are just doing a heuristic with the input natural language theorem.
Sorry. So it seems like at no point you kind of use, or there's it, you don't ever use a data set consisting of natural language theorems and formal language theorems. Like you're sort of just generating the semantic equivalence through input of other LLMs. Is there any like natural language or to formal language database that exists that you could use?
Use a
Yeah,
data set.
there is a data set. So actually, during evaluation, we are using that kind of a data set because during evaluation, we assume we have the gold standard theorem in formal language. But during inference, we cannot assume that we have the gold standard thing because during inference, we don't know what is the gold standard. So the only input is the natural language theorem proof there. So I will show the inference pipeline soon. So there we have a.
Yeah. During training also, during fine tuning, you are using a data set as well, correct? So
Yes, during fine tuning, we're using data set.
So there are two models being trained here. One is joint embedding model, and the other is the LLM itself, which is being fine-tuned. There we do have access to a gold standard data set, and during validation as well, that is used. But at inference time, when you're using it in the wild, you don't know what the gold standard is because you're translating it for the first time, right? You're given some natural language statement and proof pair, and then you want to translate it into lean.
Yeah.
Keep
So
going.
this is the detailed algorithm that we use for the iterative proof pair. So as I mentioned, the LLM generates the initial formal theorem proof pair from the input natural language. And we perform syntactic verification using Lean's type checker and semantic verification using the original natural language theorem. And if either of these fail, we trigger an iterative repair loop. So the LLM receives the feedback on which checks failed and then attempts to correct that proof. And the process repeats up to a maximum number of iterations. In our case, we are using 5 iterations at the max, or stops early if both checks fail. And so essentially, it allows the model to refine the output until we have a fully type correct and semantically aligned formal proof, or declare failure and give the best guess if it cannot converge within the allowed iterations. So now that we have covered the proof-rich pipeline, let's move to the experimental setup. Here I'll describe the dataset and the metrics. So for training proof-rich, we prepared a dataset called NuminaMath Lean PF. So this builds on existing high-quality dataset NuminaMath Lean and NuminaMath 1.5, which are available on Hugging Face. And the NuminaMath 1.5, it contains a large collection of math problems. From this, the NuminaMath Lean was derived. So it is a subset of 104,000 instances covering competition level problems in algebra, geometry, number theory, etc. And to prepare our dataset, NuminaMath Lean, so which is specialized for proof auto-formalization, we first perform formal verification and repair. So for each formal statement and proof, we type check it using Lean version 4.15. And we found that around 6% of them failed. So we repaired them using Gemini 2.5 Pro while extracting the error message. And next, we perform a natural language proof generation. So all these instances in the dataset, they didn't contain the natural language proof. So we had to generate it ourselves. So for 25,000 instances, we retrieved an informal proof sketch from the dataset. And these were just a proof sketch. They do not qualify as a natural language proof as such because they were much less detailed. So then we used Gemini 2.5 Pro and translated the formal proof to a detailed natural language proof. And we found that like if we are translating formal language to natural language, it's much more probable to be correct than if we do the opposite way. So the resulting dataset, it contains 38.9 thousand instances with informal statement, informal proof, formal statement, formal proof. And for validation, we prepared the MiniF2F PF dataset. And there are two main versions of MiniF2F. So one for Lean 4.15 and one for 4.20. And one contained the informal and formal proof, other was missing. So we joined these two dataset, and finally we had a consolidated dataset suitable for evaluating our system's ability to validate our tool on proof auto-formulation. And now coming to the experimental evaluation and the results. So starting with the natural language to formal language cross-model retrieval performance. So first we evaluate the cross-model retrieval component in two directions. So in the natural language to formal language direction, we given a natural language theorem proof pair as input, we check whether the model can correctly retrieve the lean counterpart from a large database. And symmetrically in the formal language to natural language direction, we check whether the formal language input is retrieved given the natural language counterpart. So a retrieval is counted as successful if the correct counterpart appears in the retrieved set. And we use four main metrics here. Recall at K is the percentage of queries for which the correct counterpart appears within the top K retrieve results. Mean reciprocal rate rank, it gives a fine-grained notion of ranking quality. So it's average the inverse of the rank at which the correct match appears. And we also do a cosine similarity analysis where we directly inspect the embedding space. So what we do is we compute the cosine similarity between the query and the top K retrieve candidate and report the mean and the interquartile range for this. So we also measure the cosine similarity against non-retrieved items also. So we have the cosine similarity with the retrieved items and the non-retrieved items. And together, these metrics tell us whether the retrieval is successful or not, or how well it is. So now, to the best of our knowledge, no prior model exists that jointly embeds natural and formal proofs into a shared space. And as we know, building such a space is hard, and standard encoders, they're trained to treat input as a raw text, not accounting for the formal proof structure. But instead, we use the DAG structure while encoding the formal proof. So we compare against a strong baseline, which we call as the SOTA encoder. So here we use the sentence transformer all mini LM model, and it treats both natural language and formal language as plain text. And this baseline helps us measure how much benefit comes because of our joint embedding model. So for performance comparison, I'll not go through all the values in the table, but just state some of the major insights. So as we observe from the results, the SOTA encoder mainly captures the surface level textual similarity. So it does not actually learn the logical or semantic structure needed for natural language, formal language matching. But in contrast, our joint embedding model, it performs much better. So the recall at K, it improves across all the K values. So for natural language to formal language retrieval, we get around 3.28 times higher recall at 1. MRR also improves by 2.74 times. And further, we observe that the correct counterpart typically appears within the first or second rank because of this kind of training. And further, we see a substantial improvement in cosine similarity. So because of the joint embedding, the retrieve proofs, they show 23% higher median similarity, and the median similarity of non-retrieve dropped to minus 0.01, which is 104% lower. So that means the embedding space has a much sharper separation as compared to the state-of-the-art encoder. So relevant pairs cluster tightly, and irrelevant ones are pushed far apart. So now that we have seen a improved cross-model retrieval performance, we move to our main goal, that is evaluating the end-to-end proof auto-formalization. So to evaluate proof auto-formalization, we start with a natural language theorem proof pair. LLM produces a formal language theorem proof pair, and we determine whether it is correct or not. So for this, we use two metrics. One is type correctness, another is semantic correctness. So TC, it checks whether the generated formal proof is accepted by the Lean's type checker. In other words, does the proof compile in Lean without any sorry keyword? And once the proof is type correct, we move to the second metric, which is semantic correctness. So this asks if the generated theorem actually same as the gold standard formal language theorem. So here we have access to the gold standard formal language theorem because this is the evaluation time. So to check this, we test whether the generated theorem is definitionally equal to the ground truth version. So what we do is we prompt Gemini 2.5 Pro and ask it to produce a lean proof showing the bidirectional equivalence between these two statements. And we ask it to use only a restricted set of tactics. So first we use RFL. This is the fastest check and works with when both the terms are literally identical. And if this fails, we try sim for structural or trivial rewrite. And if this fails too, we use ring, so which is good for algebraic normalizations. And finally, we use a combinations of all these tactics. So here for SC, the semantic correctness, even though we are using an LLM to assess the judging step, the final validation still comes from Lean itself. So it has to come up with a formal proof of bidirectional equivalence. And before I show the results, let me briefly introduce what we compare against. So currently, there are no existing tools that perform proof auto-formalization end-to-end. To our knowledge, only two major tools exist. One is the draft sketch and proof, but it targets only Isabelle, not Lean 4. And the form L4, so for this, the paper is released, but the model is not yet available. So direct head-to-head comparison is not yet possible. So because of this, we compare against the strongest available baselines, so drawn from three categories. First is all the state-of-the-art models for theorem auto-formalization. So these models translate just the theorem statement. For example, the Key-Mina auto-formalizer, Herald translator, and this. Next, we use all the general purpose foundation models, and these serve as strong reasoning LLMs. And lastly, we compare against the SOTA LLMs for formal proof synthesis, and they generate proofs directly in Lean. For example, the DeepSeek prover, Gödel prover, etc. Now let's look at how these existing state-of-the-art models perform on the proof auto-formulation task. So first, existing theorem auto-formulation, they fail completely because they are trained to output only a theorem statement with sorry as the proof. So their correctness is 0% across all pass at K when we are evaluating proof auto-formalization. For the foundation models, in a few shot setting with pass at 32, the strongest ones we found were Gemini 2.5 Pro and GPT-5 Mini. So they get around 8 to 9% semantic correctness and around 30 to 35% type correctness. So they occasionally type check, but true semantic alignment is still very low. Then we move to the state-of-the-art formal proof synthesis models. So here, as I mentioned, we compare against some of the strongest provers available for Lean. And we found that the Key-Mina prover RL 1.7 billion, it achieves 31% SC and 93% TC. And in zero shot, actually, the semantic correctness increases, but the type correctness drops. So that means giving random in context examples, they improve the syntax, but may hurt the semantics. So that actually motivates why it is essential to have relevant in context examples while prompting the LLM. And that is what Proofbridge is designed to do. So for Proofbridge, coming to the results of our method. So first we evaluate the only SFT without any kind of retrieval. So here we get, compared to the Key-Mina model, which is our base model, we get 3.28% improvement in SC, but type correctness drops. Next, when we do retrieval augmented SFT, we get 23.77% semantic correctness improvement, but again, the type correctness is low. And finally, when we apply all the three, that retrieval augmented SFT, repair, then we get a 31% improvement in semantic correctness and 1.65% improvement in TC. So overall, Proofbridge gets like strong semantics and strong syntax, beating some of the best models in the space of auto-formulation. So to summarize, our contribution comes in three parts. First, the method. So it is a retrieval augmented framework for end-to-end proof auto-formulation. And for that, we use a natural language, formal language joint embedding. Second, the data. We curate Numina Math PF, which is 38.9 thousand natural language, formal language proofs, and also the mini F2F test PF dataset for evaluation. And these are specifically designed for proof auto-formulation, not only theorem auto-formulation. And third, the results. So we introduce the semantic correctness as a verifier grounded metric. And the Proofbridge, it delivers 31% improvement on semantic correctness over some of the strongest state-of-the-art provers. And it gets a 3.28% improvement in retrieval quality also because of our joint embedding model. So in short, we retrieve the right proofs that essentially guides the generation with relevant context, and that leads to much better auto-formulation performance. And finally, I already introduced this slide before where I talked about the challenges in proof auto-formulation, but now let me briefly discuss how we address the key hurdles one by one. So first, checking semantics. So here we use Gemini to prove bidirectional equivalence in Lean between the generated and the gold standard theorem. For reducing hallucination, we propose joint embedding plus retrieval augmented fine-tuning so that we can give like rich context to the LLM. For data scarcity, we curated these two datasets, the NuminaMath Lean PF and the Mini F2F test PF with type-checked theorem-proof pairs. Further, we have an end-to-end proof auto-formulation pipeline instead of separate theorem formalization and separate proof synthesis. And we retrieve semantically relevant Lean proofs that actually guides the generation process. And finally, for incomplete natural language proof, we introduce iterative proof repair. But in the future version, we also have plans to incorporate Vern or blueprint style intermediate representation to make the process more streamlined. And now, before concluding, I'll briefly talk about another technique we have developed, which is RLSF, that is reinforcement learning via symbolic feedback. And while this was originally proposed in the context of code generation, we believe it is highly relevant for mathematical reasoning as well, especially in a neuro-symbolic setting where verifiers and feedback loops are central. So in one of the recent papers, we proposed a corrective feedback loop between LLMs and automated reasoning engines so that can perform code translation. For example, translating a whole program from one high-level language to another, for example, Java to Python. And this diagram shows the overview of our approach. So we have two types of feedback here. There's scalar fine-grained feedback. So one is the compiler feedback that tells the LLM how close the generated program is from being perfectly compilable. Another is the symbolic execution feedback. So it tells how closely the generated program in Java is equivalent to the input program in Python. And both of these are scalar feedback. We use reinforcement learning to incorporate them during fine-tuning. And overall, we found that such carefully designed logical feedback during fine-tuning, it significantly improves the LLM's ability of translating code or in general, producing any formal language object. And in another recent paper that got accepted at EKI this year, so we proposed RLSF, that is reinforcement learning by symbolic feedback. And it is a new fine-tuning paradigm for LLMs, where the LLM acts as the RL agent, and the environment is enhanced with sound symbolic tools, for example, solvers, provers, etc. And the main differentiator is that the symbolic reasoning tools, they generate polynomial size certificate that identify errors in the LLM generated object, and these certificates are transformed to a fine-grained token level feedback. So instead of a scalar feedback, we use a vector reward that precisely identifies the erroneous tokens in the output and produces a fine-grained token by token reward. And we demonstrated the usefulness of this in tasks like program synthesis, molecule generation, mathematical problem solving, etc. So for example, if you show this example for applying RLSF in the code generation problem that is given a natural language pseudo-code, we want to generate a C++ code. So during training, when the LLM produces a C++ code, we pass the C++ code to a compiler and a test suite, which identifies the erroneous lines in the code. And for each erroneous line, we give a very low reward for the erroneous lines, for all the tokens in the erroneous lines. And for all the tokens in the non-erroneous lines, we give a high reward. So now the LLM is basically trained to, and it gets to know during training that which lines are erroneous, which lines are not, and it can actually tune itself to produce non-erroneous lines. So finally, the LLM is trained to produce more compilable formal language objects. And we believe that these are very relevant in the AI for math setting as well. So finally, I'll provide some concluding remarks. So to conclude, ProofBridge is an end-to-end framework for proof auto-formulation in Lean 4. It combines natural language, formal language, cross-model retrieval, then retrieval augmented fine-tuning, and also iterative proof repair guided by the verifier feedback. And it ensures that the generated lean proof, they're both semantically correct and syntactically correct and semantically faithful. And looking ahead, our long-term goal or vision is a neuro-symbolic AI for math ecosystem. And we want to build a unified framework that can handle proofs of any size by dividing them into smaller lemmas and formalizing step by step. And we plan to leverage a specialized intermediate representation, retrieve semantically relevant formalizations through joint embedding, and support multiple backends like Lean, Isabelle, Coq, etc. And the ultimate goal is to populate all the formal libraries such as MathLib, the archive of formal proofs, etc., for making formal mathematics more accessible and scalable. And in short, we want to retrieve smartly, formalize step by step, and repair iteratively towards a fully automated math reasoning ecosystem. So that was all. Thank you so much.
Are there any questions?
Yeah, I had a question. So at inference time for semantic equivalence, you're using Gemini as an evaluator.
Yes.
So I'm wondering, have you considered, or is there any thought given to the idea of like sort of having a sort of purpose-built evaluator rather than just sort of an out-of-the-box LLM for that task?
Yeah, we can also train a judge, an LLM judge, that can actually take a natural language theorem and a formal language theorem and give a score of how equivalent they are and identify like errors, like if they can find any errors between the natural language and the formal language part. But I think, yeah, for this we tried a foundation model, but in the future that will be a good idea to specifically train an LLM for this kind of judging function.
Yeah. Just to add to Aaron's question and Prithwish's answer, a similar LLM judge was actually used in a recent auto-formalization attempt at Morph Inc., where they auto-formalized a version of the ABC conjecture, which was proved by Jared at Lichtman at Stanford, and two of my students helped auto-formalize that theorem and proof. And there they did use this kind of LLM judge so that this idea has been used in other settings. But I just want to add to the limitations of the tool. So one limitation is what Aaron already kind of zeroed in on, which is we are using a off-the-shelf foundation model for semantic equivalence. Ideally, you want to use a more fine-tuned or formally trained model for this particular task. So that's one limitation. Another limitation was pointed out by Castra, which was the cross-modal, the joint embedding model is still fairly small because this was limited by the resources we have. But in the longer term, we want to have more resources to be able to train a much larger model, because the kind of proofs we would like to support would be, from textbooks like Wilfred Hodge's book and so on. We are not nowhere close to that at this point with these kind of resources.
But are you equipped to do live demos? Maybe not now, but in general, like, can we see this actually happening, or like at least some example of like what theorem and proofs
sure.
have been translated? Like, what is
Prithwish, go ahead.
Yeah, sure. We can have a live demo, or I can also send some examples of how the retrieval system is happening. What are the top K retrieved proofs that are actually helping the LLM to generate?
Yeah, can you do a demo right now?
I don't think I have an example right now. I have to set up the.
Okay. So one thing you want to do is definitely release the code to Matthias and Aaron, and also maybe prepare a live demo, maybe record it in a video, and then.
Yeah, that would be good. Yeah, so everybody can watch.
Yeah.
We can add it to the recording of the talk or something. Yeah.
Right.
Okay, sure.
Okay. Any other questions?
Yeah, I just had another question too, just sort of somewhat related to the first one. So when you're doing the, I guess, repair process in inference, it seems to me at least like you might sometimes encounter, I guess, situations where it just sort of never resolves.
During inference, yeah.
Or just sort of like seriously degrades in the name of trying to find something that type checks correctly. Does that happen? And like maybe is like strict type checking like a really strong constraint to be putting on that?
Yeah, it's a strong constraint, but during iterative proof repair, we have a maximum number of iterations that we want to limit the model to. And what we do is like, so this is one trial of iteration, but for evaluation in the table, we use like pass at 1 to pass at 32. So LLM is given like 32 attempts at providing the formalization. So we are seeing that like when the LLM is given more and more attempts, it finally comes up with better and better results compared to only one attempt.
Yeah, just to add to that, although you do want the type checking to be strong though, like I don't think you can skip that part at all, like because otherwise you're going to get pairs that are proofs that are not proving the theorem, right? So the type checking, even though it's a very strong constraint, I think you do want that. Maybe.
Yeah, for example, in a like code generation problem, the first requirement is that the code has to compile. So here, the first requirement is that the output theorem proof pair has to be type checked. Then on top of that, we are coming with the semantic equivalence. But I think type check is the essential thing we want to achieve.
I guess sort of related to Deirdre's question earlier, it seems to me that yeah, like type checking for the theorem statement, I totally see why that is very important. Whereas perhaps allowing proofs that have some limited use of sorry, but otherwise type check, like you might, for example, get significantly better proof statements, but if you're putting like a type correct proof as a barrier to getting a formalization of the statement, then that could be sort of imposing an artificial barrier.
Yeah, that's true. That's why I think in the in this pipeline. So here, what we want to do first, we want to structure the proof step by step, and then have a skeleton lean proof with sorries in place for this is a block by block translation of each natural language block to formal language block, but we have sorries in place. And then in the final step, we want to do a proof synthesis of this. But for this, we will utilize the natural language proof 2 as an additional context during proof synthesis.
Yeah, no, I think that's a very good point, Aaron. Yeah, that makes perfect sense.
So I mean, the sketchy part, obviously, although it's still reasonable, is like using the LLM to judge semantic equivalence. Do you guys do any like spot checking or sample a few and human check them to see what the error rate of it, like false positives?
Yeah, we did some human evaluation, and whenever the Gemini is providing some bidirectional proof of equivalence between the generated theorem and the gold standard theorem, we found that they're always correct between these two because we are restricting the set of tactics that the LLM can use in providing this bidirectional proof.
But the statements are still, you have to human, if you don't human check them, you're relying on the LLM to know that the statements are correct, right?
No, during evaluation, we have access to the gold standard theorem.
What I'm saying is like the equivalence of the natural language of the statement to the lean statement.
Okay, yeah. Yeah, we are assuming that in the data set, the pairing of the natural language and formal language is correct. Like we are assuming that to be gold standard.
I see.
But I think your concern is valid. Like when the proof sizes start growing, right? I don't know what the maximum proof size here is, Prithwish, in the data set. Like how many tactics are we talking about? Do you recall?
No, I don't recall at the moment.
Wait, so maybe I should clarify, can you go back a few slides? I don't know which slide it is exactly, but one of the pipeline slides. It might be early on, but it might have been multiple times. So this, sorry, wait, next one maybe. Yeah, so here, like the Gemini step here to say that this is equal to this, right? Wait, so is this the lean proof here or no?
No,
Yes.
Gemini doing a lean proof, or is this just checking natural language?
It's checking
It's just
if the
doing a
lean
natural
proof
language
is
reasoning.
equivalent to the natural language.
Yeah, so in this
Yeah.
step, like, did you human check how accurate Gemini is here? Is what I'm curious about.
I mean, we
Yes,
spot check sometimes, but not for every pair because there are too
Yeah,
many.
obviously you can't check every pair, but I was wondering, like, did you actually like
Yeah,
like
we
get
did.
an error rate on Gemini here or no? Or you just checked a few and it was always correct?
When we checked it, yes.
It was always correct. Okay.
Yeah, because finally we also have the evaluation pipeline where we are doing the bidirectional proof of equivalence in Lean. So this is just for inference, but after all this is done, we are evaluating in the table whether there is actual equivalence or not.
Yeah, but so I'm confused. Okay, so it's just with the data set, like not like if it's on the test set, then you care. I guess all of these have already been checked because you're only using data sets. You're not doing any. So that's why you can trust the.
Yeah,
Okay.
right.
That's exactly right, because we are using a well-prepared, well-curated
Yeah,
data.
if it was like a new thing, then you couldn't necessarily trust Gemini here, right? That's what I
Right.
missed. I see.
Yeah,
So because
That's,
it's
that's exactly
proprietary,
right.
you don't care. Okay, that makes sense. Yeah, sorry.
You couldn't trust Gemini 100%, no.
Yes.
Yeah, I see.
And one of the things we want to do next is to expose the system to real life scenarios.
Yeah.
That's where Matthias and Aaron and other users come into play, is to be able to expose the system and find the bugs and find the weaknesses and then fix them as we go along. Yeah.
Yeah, sure. One more question. Yeah.
So, I'd like to come back to the question of how to compartmentalize. Deidre mentioning earlier that you could start from theorem to theorem instead of considering the pair. It seems to me that it's important for a number of reasons. First, what is the data set that is used to train, given that the map may be first theorem to theorem before before going to the pair. This kind of question, it seems to me that is particularly important when you attempt to go beyond the small set that you have now, and you want to generalize to bigger theorems or more general theorems. You mentioned that you want to subdivide perhaps in lemmas and so on and so forth. So that problem then would come back, because depending how you subdivide, what data is then going to be used in order to train, in order to ask and then answer the questions that lead to the map on the basis of the smaller lemmas. On one hand, it's good to have a pair because there is learning that goes on in informing, perhaps reducing the problem of hallucination. But on the other hand, there's more information that somehow needs to be organized. What is the fundamental technique, or what's the fundamental organization to be able to assess what is the actual strategy that gives you a better map from natural to form?
So let me take up that question. So I completely agree with you. When we go to richer settings, it might be better to try to assess the pipeline on just statement formalization before you do statement pair formalization, especially if the statement proof pair formalization. In particular, if the proof is if the proof is like totally unstructured. So in that scenario, you first want to evaluate on statements. I think your second question, correct me if I'm understood it properly or not. I think what you're saying there is that this evaluation structure may not lift to real world settings, because here you're guided by a curated data set. When the question I think is, how would you come, what kind of evaluation would you come up with that could then enable you to trust the tool chain for real world setting? Like, is that fair? Did I get that right?
That's fair, yes, because the data set is then going to be, as you said, less prepared or less targeted,
Yeah. No,
adding more possibility for hallucinations or information that turns out to be perhaps more noise
Right.
than actual information to enable you to map with the same level of accuracy. So
Exactly.
could it mean that the human oversight, the human supervision would become much more important?
Absolutely. I mean, I think that we will need a very strong human supervision. And I don't have a good answer beyond that at this point in time. It could be, one possibility could be to have like competing tool chains and different teams, like looking at the same auto-formalization challenge. You could also have, you want to allow for different backend theorem provers like Lean and Isabel and so on, where completely different sets of people, different proof paradigms are looking at this auto-formalization paradigm. So all these kind of interventions are needed in order to have any sort of industrial strength tool to address the kind of questions that you're asking.
Thank you.
Okay, I guess that's it. Thank you everybody for coming to the third talk. Do you want to say something?
No, just,
No,
yeah,
that's good.
I agree. Thanks,
Yeah,
everybody.
that was a great talk.
Thank you so much.
I really enjoyed it. So thanks a lot. I appreciate this very much. So Jared, in fact, might be the next speaker. Yeah, thank you. Great job. Yeah, the next talk will be like in 1 or 2 weeks. I will send an email so we can hopefully this build up. But this was a really great start for the seminar. Thank you. Okay.
Great.
See you
Thank you so
soon,
much.
everybody. Yeah, bye.
Bye.
All right, very good.
Yeah, thank you guys. But yeah, they have to. I don't know. I want to see like what they actually can do.
Yeah, that we didn't get a sense at all. I mean, he was talking about the ABC conjecture, but are they really? I mean,
No, these guys now they're going to share it. Somebody else.
Yeah,
somebody else is
And
doing.
those guys are not using this. Yeah, I don't know, like,
I think it's like Jared proved that, like, because there's a trivial bound that's like 2/3, and he improved it to like 2 or 3 percent exceptions or something like this. And like the actual ABC is like that there are finally many exceptions. So it's like the percentage of exceptions or something. They did like a slight improvement and then did a formal proof of the trivial bound 2 or 3. Yeah. But like,
But it's not auto-formalizing it.
No,
it is, but Jared wrote like an extremely detailed blueprint, and anytime the LLM had like troubles, he would rewrite that step. So it's like extreme human supervision, but
Yeah.
Jared himself did not write any code. Yeah. I guess he'll talk about it, but yeah.
you don't have to turn anything off, right?
I think Brian will take care of everything.
No. Yeah. So at the beginning, it took me a while until I could actually understand it. So it's not my field at all. So we think we are the same, so it's epsilon. Epsilon going to zero.
Something that it would relate to.
Not at all, even more. Thank you, it's zero.